Hello everyone. Today's topic is dual nature of radiation and the de Broglie's hypothesis. So, to understand the dual nature of radiation, what we know that the particle nature of radiation, the particle nature of radiation can be explained based on photoelectric effect and the Compton effect. And the wave nature of radiation can be explained based on the interference polarization diffraction and the reflection phenomenon of the radiation, that is the electromagnetic radiation. So, the particle nature of radiation can be explained based on photoelectric effect and the Compton effect, and the wave nature of radiation can be understood as the radiation undergoes interference, polarization, diffraction, reflection, etc. So, what we know that light is one kind of electromagnetic radiation. Light is a kind of electromagnetic radiation. So, in 1905, Einstein suggested that as the light is a stream of moving photons, light is nothing but the stream of moving photons, and photon is a particle, and light undergoes interference, polarization, diffraction, refraction, other phenomena. So, Einstein said that the light has both particle and wave nature. So, all the electromagnetic radiations can also possess particle and wave nature, and this phenomenon was known as dual nature of radiations. As light is a kind of electromagnetic wave, in 1905 Einstein explained that the light possesses dual nature as it has both particle and wave like nature. So, all the electromagnetic radiations also possess wave like nature, and this phenomenon it was known as dual nature of radiation. So, based on the concept of dual nature of electromagnetic radiations, de Broglie in the year 1920 suggested that all material particle like electron, proton, neutron, alpha particle and so on, many other material particle in motion possess wave-like nature. The de Broglie hypothesized that all material particle, for example, electron, proton, neutron, alpha particle, beta particle, all the elementary particle, all microscopic particle which we study under the head of quantum mechanics in motion. This is very important. When it is in motion means when it is in the moving state, not in the stationary condition. When in motion possess wave-like nature, and this concept was known as de Broglie hypothesis. So, if the particle possess wave-like nature, then it must be associated with the wavelength. So, these particles which possess wave-like nature, the material particle or the particles which have or possess wave-like nature was called as matter waves, and the wavelength associated with these particles and the wavelength associated with these particles was named as de Broglie wavelength. And de Broglie suggested that the measure of wavelength lambda is equal to h by mv, where h is Planck's constant, m mass of the particle, and V is the velocity of the particle. So what it is? The particle, the material particle which which possess wave like nature was known as matter waves, and the wavelength associated, if we denote that wavelength by lambda, the wavelength associated with these particle was called or named as de Broglie wavelength, and the expression can be given by, expression for wavelength can be given by lambda is equal to h by mv, where h is Planck's constant, m is mass of the particle, and v is the velocity of the particle. Now what we know, the product of mass and velocity is known as momentum, which we denote it by p. So lambda can be also expressed by lambda is equal to h by p, where p is the momentum of the particle. P is the momentum of the particle. Now let us see how can we derive this expression lambda is equal to h by mv using the Planck's law and the Einstein mass energy relations. Expression for the de Broglie wavelength. So what we know, that Planck's law, using the Planck's law, the energy of a particle is given by, means the energy of a photon, if we assume it, it is given by E is equal to h nu, and that is equal to hc by lambda, where as usual h is Planck's constant and c is the velocity of light. Velocity of light. Planck's law, we can write the, using the Planck's law, we can write the expression for the energy of a photon. Energy of a photon, not energy of an energy level. When we write energy of an energy level, then we have to introduce n, first level, second level, third level, and the difference of energy between the two levels give the energy of a photon. So E is equal to h nu, and nu is the frequency of radiation, which is equal to hc by, which is equal to c by lambda. So E is equal to hc by lambda. Now other thing what we know, that Einstein mass energy relation, as per Einstein mass energy relation, E is equal to mc square. What Einstein has explained, when the particle moves, then the mass of the particle changes. That is also we call it we discuss in relativistic theory. But as we know, for ourselves or for anyone of else, when we walk or when we move, the mass remain stationary. But Einstein suggested that for the elementary particles, which one, if you can assume photon, when it moves, the mass of it changes, which was given by the relation m is equal to m naught divided by square root of 1 minus v square divide by c square and whole to the power half. Half 1 minus v square by c square, the denominator term we take square root of that. So, E is equal to mc square. So, what we see that this what we see that equation 1 and 2 gives the energy of a particle. So, we can equate the term which is in the right hand side. So, from equation 1 and 2, we can write Hc by lambda is equal to mc square, or H by lambda is equal to mc, or lambda is equal to H by mc. But what we know, elementary particles do not have the velocity as compared to the velocity of light. If we assume that v is the velocity of the material particle, v is the velocity of the material particle, then we will replace c by v. So, replacing c by v means v is the velocity of the material particle and c is the velocity of light. So, replacing c by v, we get lambda is equal to h by mv, or lambda is equal to h by p, where p is the momentum of the material particle. So, this expression 4, as already explained, is the expression for equation 4, lambda is equal to h by mv, or lambda is equal to h by p, is the expression for de Broglie wavelength. So now we will derive the expression for the de Broglie wavelength for the accelerated particle. So, if the particle is accelerated by voltage V and it has the velocity V, the mass of the particle which is accelerated is m, then we can write charge multiplied by the voltage. E is the charge of the particle and V is the voltage applied. This is what we know as, it is potential energy of a particle, that will be equal to half mv square. EV is equal to half mv square. Now, we will further solve this equation, that will be equal to half, multiply and divide this equation by m. So, we will get m square v square divide by m. So, we can write E into V is equal to P square by 2m. Now taking the expression for de Broglie wavelength, what it is? Lambda is equal to h by p, or p is equal to h by lambda. P square will be equal to h square divided by lambda square and 1 by 2m. P square, lambda is equal to h by p, so p will be equal to h divided by lambda. Square it, p square will be equal to h square by lambda square and retain 2m. So EV will be equal to h square lambda square into 1 by 2m. So if we solve this, we get lambda is equal to h by square root of 2m EV. Also write lambda is equal to h by square root of 2m E, where E is equal to charge multiplied by the potential. Now let us take the example of electron. What we know, charge of the electron is 1.6 into 10 to the power minus 19 coulomb. While solving, we know the charge of the electron is negative, but while solving we neglect the negative charge, will not substitute the value of negative value, and we have to stop the problem. And mass of the electron is 9.1 into 10 to the power minus 31 kg. So if we solve for the electron, wavelength of electron, that will be equal to, substitute the value of Planck's constant 6.625 into 10 to the power minus 34 divided by square root of 2 into 9.1 into 10 to the power minus 31 into 1.6 into 10 to the power minus 19, 1 by V, 1 by square root of V. Take the calci, substitute these values, what you get? Lambda E is equal to 1.229 into 10 to the power minus 9 divided by square root of V. So you can substitute the voltage value as what is given in the problem, and if you remember that the value of the constant, which will be for only for electron, if the particle changes, the value of charge it will change, mass also it will change. So if you calculate this value 6.625 into 10 to the power minus 34 divided by square root of 2 into 9.1 into 10 to the power minus 31 into 1.6 into 10 to the power minus 19, you will get, and hope you got, 1.229 into 10 to the power minus 9, and when you divide by square root of the voltage value, you will get the wavelength of the electron. Wave function, which we denoted by the letter psi. So in the wave theory or in wave mechanics, we define a wave by a mathematical equation y is equal to a sin omega t minus kx. So similarly, as I have explained in de Broglie hypothesis, the material particle in motion have wave-like nature, and the wavelength associated with that material particle we call it as de Broglie wavelength. Now, for such material particle means the particle which has wave-like nature as well. So, in quantum mechanics, the variable quantity which describes the physical characteristics of a matter wave, we call it as wave function. So, in quantum mechanics, the variable quantity which mathematically describes the wave characteristics of a particle is known as wave function. So, in quantum mechanics, the variable quantity So, in quantum mechanics, the variable quantity which mathematically describes the wave characteristics of a particle is known as wave function and is denoted by psi. And the mathematical function psi a exponential of minus I omega t minus kx. Psi is function of both the position and the time. How we can define psi? Psi gives the probability of finding the particle at a particular position at a particular instant of time t. So, the psi defines the probability of finding the particle at a particular point in space. This is one dimensional space. So, it is x. If the equation is 3 dimensional, then it is a function of x, y and z. So, psi defines the probability of finding the particle at particular point in space at a particular instant of the time However, what we can observe that psi is a complex number. This psi, as minus I term it is here, it's complex in nature. Psi is complex in nature, hence has no physical significance. Psi is complex in nature and hence has no physical significance. So then how we can extract the value? What we have to do, we have to multiply psi by its complex conjugate. So, so to study the physical significance, first what we define, the probability density, and second the normalization. So the probability density, as I explained that psi alone does not find any physical significance. The physical significance of it is when it is multiplied by its complex conjugate. So this interpretation, the physical interpretation of psi, of the wave function psi, was given by Max Born in the year 1926, and he only suggested that the only quantity which has a physical significance is psi star into psi is equal to psi square, where psi star is complex conjugate of psi. Thus, how we define the probability density? It is a quantum mechanical method which gives the probability of finding the particle, which it's a quantum mechanical method which gives the probability of finding the particle at a particular point at a particular instant of time t. So mathematically how we can describe it? If we have a small volume V and in a small volume d tau, the particle is confined. So how can we express this mathematically? Psi r. Now this r is denotes the x, y and z coordinates. R denotes the location in space. R denotes the location in space. So psi rt square, when you take complex conjugate of psi, it is equal to psi square. So that gives the probability of finding the particle in the volume element d tau. In the volume element d tau, where d tau is equal to dx into dy into dz. About any point r, at any time t or a particular instant of time t. And how can we write? The probability we have denoted by p, means probability of finding the particle in the volume d tau at a particular point at a particular time, that is equal to psi square d tau. What we know, psi is a function of the position and time. So, in general we can write it as p d tau, as we understand that it is function of location and time. It is a function of location and time. So, if it is one dimensional, x, y or z. If it is two dimensional, then x, y, y, z, z, x. And if it is three dimensional, then we have to take x, y and z direction. So, p d tau is equal to psi square d tau. So, psi alone, psi which we have written it as psi is equal to a exponential of minus I omega t minus kx. So, a is the amplitude of the wave function. So, as alone it does not find any physical significance, as it is a complex number. So, we have to multiply by its complex conjugate, that is psi star, which if we consider a small volume where the particle exists, then the probability of the finding the particle will be equal to psi square d tau. So, let us see how we can find what could be the probability. If the particle exists in the certain space or in certain volume, what will be the probability value? So, that we find out when we normalize the wave function. So, in the normalization process, to find the probability value, we integrate the wave function in the limit where the particle is present. And if the particle is present in the particular volume, so within the limit, the normalization of the wave function will be equal to 1. Means if the particle is present in a definite volume tau, if particle is confined in this room where the volume of the room is tau, then we have to integrate psi square with respect to d tau within the limit 0 to tau. And if the particle is present in the definite volume, the integration of psi square with respect to d tau, it will be equal to 1. And if the particle is suppose present anywhere in the space, then what will be the limit? Anywhere in the space means what will be the limit? Minus infinity to plus infinity. So integration of the wave function means integration of psi square with respect to d tau in the limit minus infinity to plus infinity, it will be equal to 1. Minus infinity to plus infinity, if you integrate psi square with respect to d tau, that will be equal to 1. And if the particle is not present, then the wave function value, it will be equal to 0. So if you solve the wave function, means the psi square, it will be equal to 0. So it is just an on and off condition. If it is switched on, we write in digital sign, it is equal to 1, and if it is closed, then we write it is 0, or if it is off, we write the digital signature as 0. So we can say that if the particle is present in a definite volume, then the probability of finding the particle, it will be equal to 1, and if not present, then it will be equal to 0. Properties of the wave function. So this wave function actually we solve using second order differential equation. So there is not one such single solution. So based on the properties of the system, we can discuss which answer is acceptable, just like a quadratic equation. So what is the properties of the wave function? We must know, so that we can say that this particular function is a wave function, means it describes the material particle, the function which describes the material particle. So first is psi must be single valued everywhere. Now let us consider a function fx and draw the function fx with respect to x. Let the solution be this. What we see at a point q, there are 3 values for this wave function. So such a function we cannot say it is a wave function. For it to be a wave function, it must have a single solution, single value at any point. Next is psi must be finite everywhere. Psi must be finite everywhere. So if we draw the wave function, and at point q, what we observe that the value of the function is approaching infinity. So such function also we can't say that it is a wave function. For a function to be called as wave function, it must be finite at each point. Next, psi and its first derivative must be continuous everywhere. So let us draw the function. What we observe here that the function at point Q is discontinuous. The function at point Q is discontinuous, and hence what we can say here as well that this function is not a wave function. For it to be a wave function, both psi and its derivative, means if you differentiate with respect to any term, it must be continuous everywhere. And finally, the fourth one, in the bound state, if psi vanishes, means if psi is equal to 0 at certain point at infinity, so the value of psi star, so the value of psi star into psi must also vanish at infinity, where psi star is complex conjugate of psi. So what are the properties? Psi must be single valued everywhere, psi must be finite everywhere, psi and its first derivative must be continuous everywhere, and in the bound state, if psi vanishes at infinity, so must psi star into psi, where psi star is complex conjugate of psi.